Hello. Okay, let's talk about symbolization in predicate logic. When we're faced with a quantified sentence in English and we want to find a symbolization in PL, there's a series of steps we can follow, at least while we are learning the process. First, we start with a paraphrase. In this paraphrase, we make our sentence quantify over the whole domain, that is, all the different values of x. Later on, you'll see what I mean by this. Then we restrict our domain by using the is such that locution. Last, we associate each quantifier with a particular connective. Let's start by applying these steps to existential statements. Okay, so we have some f is g. We could also start with there is an f that is g, which is another typical existential statement. But let's start with some f is g. Okay, the first step is that we're rewarded with the is such that phrase. So notice that I'm emphasizing in italics the words that are eventually going to be substituted by variables. Then you have this sentence. Some x is such that x is f and x is g. Here we have divided the whole sentence in two. The quantifier variable pair, which is in parentheses, and the rest of the sentence. And when you eliminate the fluff, this maps straightforwardly into a predicate logic sentence. You have there is an x, and then fx gx. And this is what you end up with as your symbolization. Let's give a specific example. Some dogs are sentimental. So you start by paraphrasing, by saying something is such that it is a dog, and it is sentimental. And then, one step towards logic keys, we have the quantifier phrase, some x is such that x is a dog and x is sentimental. We have added the variables. And then we replace the English phrases with the symbols. There is an x such that dx and sx. This PL sentence will also represent other kinds of English sentences, such as there is a sentimental dog, or there is a dog who is sentimental, or at least one dog is sentimental. All of these sentences will also be represented by that PL formula. Okay, so why do we have to use the ampersand as a connective? Well, the reason is that neither of these is true in the same situations as some dogs are sentimental. So they aren't really good symbolizations. So let's imagine this situation. We have two individuals. One is Rex, the other one is Lazarus. Rex is a dog and is unsentimental. Lazarus is a cat, therefore not a dog, and is also unsentimental. And notice that here, some dogs are sentimental is false, because the only dog that exists here is Rex, and Rex is not sentimental. Therefore, all symbolizations of some dogs are sentimental must be false. That is a requirement, that if a symbolization is going to be correct, it must come out false in this situation. So, Rex is a dog is true. So if we symbolize it, we have dr, which again is true. But if so, Rex is a dog or Rex is sentimental is true by the evaluation rule of the V. That means that this sentence is also true. Then there is an x such that dx or sx is true. This is the equivalent of the sentence that we have used as a symbolization, but the only difference is that we have the V instead of the ampersand. That's all the difference. However, remember that some dog is sentimental is false. So this sentence is an unacceptable symbolization of some dog is sentimental. So there is an x, dx, or sx is an unacceptable symbolization of some dog is sentimental because they are not true in the same conditions. But what about the horseshoe? Remember that this sentence, there is an x such that if it is dx, then sx is equivalent to there is an x, not dx or sx. But then if you look at Lazarus, we know that it's not a dog because it's a cat. Therefore, not dl is true. Then, again, not dl or sl is true, again by the evaluation rule of the V. Therefore, if dl, then sl is true. And so there is an x, if dx, then sx is true. But again, some dog is sentimental is false. So they are not true in the same situations. So this is not a good symbolization of the English sentence. However, there is an x, dx, and sx is only true when some dog is sentimental is true. So this is appropriate. Okay, now let's go to a universal statement. Let's suppose that we start with every f is g. Then again, we do the paraphrase. Everything in the domain is such that if it is f, then it is g. Then we get closer to predicate logic syntax by separating the quantifier and a variable. Every x, and then it's such that if x is f, then x is g. And then again, when you eliminate this fluff, you get something that again maps quite directly to PL syntax. You have a quantifier sentence and then a bound conditional sentence. And this is what you end up with. Every x is such that if it is f, then it is g. This sentence will also work as a symbolization of all f are g, or each f is g, or any f is g. So let's give an example. Every pig is remarkable. The next step is to paraphrase. Everything is such that if it is a pig, then it is remarkable. Then every x is such that if x is p, then x is r. Then the last step, for every x, if x is p, then x is r. And we can answer the same question here. So why the horseshoe and why not other connective? Well, none of the other connectives work. If you had the ampersand instead of the horseshoe, you end up with something like everything is a remarkable pig. And so suppose that you have the situation. Now we have three individuals. Babe, who is a pig and is remarkable. Chris, who is a pig and is remarkable. And Dolly, who is a rabbit and is unremarkable. In this situation, every x, px, rx is false. Why? Because Dolly is not a pig. However, every pig is remarkable is true, because there are two pigs, Babe and Chris, and each one of them is remarkable. So that means that there is a discrepancy between the truth value of our symbolization and the truth value of the English sentence that we want to represent. So this is not a good symbolization. What happens if we have the disjunction? Then what we're saying is that everything is either a pig or is remarkable. But this sentence is false, again, because Dolly is neither a pig nor remarkable. But then again, every pig is remarkable true. So the disjunctive sentence is not going to work. So neither of these non-conditional symbolizations of every pig is remarkable is acceptable. But the conditional one is preferable because it comes out true in this situation and it comes false in this other one. And the difference is that whereas Babe and Dolly are the same, now Chris, although still a pig, is unremarkable. So it is equivalent to nothing is both a pig and unremarkable. Or if you want to say it in a more English-like way, nothing is an unremarkable pig. So this is going to be our standard way of symbolizing universal sentences. Okay, scope interactions. Some English sentences contain both quantification and negation. And here we have to pay attention to where we place the quantification and negation symbols when we're doing PL symbolizations, because order matters. For instance, take our last sentence 4. Every x is such that if it is p, then it is r. Then we could have the negation at the beginning, fronting the whole sentence. Or we could have it here just before the consequent. Now, this is going to make a lot of difference to the interpretation of the sentence. Let's focus on the contrast between these two formulas. So here, the scope of the negation is the length of the red horizontal bracket. And here, you can see the scope of the universal, which is in blue and is much shorter. It's just what is to the right of the quantifier. But if you look at 6, the roles are reversed. Now, the quantifier has the whole open sentence, the whole body of the sentence, as its scope, whereas the negation only has the sentence Rx. And here, the quantifier has wide scope with respect to the negation. So, again, let's see how we interpret this sentence 5. We would render this in English as, it is not the case that every pig is remarkable. Why? Because it is just 4, but negated. It's just, you take sentence 4, and then you place a negation on the front. Now, more idiomatically and preferable, we would say, not every pig is remarkable. And this is a situation in which sentence 5 is false. Why? Because every pig in existence is remarkable. But if you look at this other one, it is true because there is at least one pig that is not remarkable. So there is at least one thing that is a pig and is unremarkable. Now let's look at the other one. In English, this would say no pig is remarkable, or in a way that matches more closely the PL syntax, every pig is unremarkable. And again, on 5, the negation has wide scope, and on 6, it has narrow scope. And this leads to two very different interpretations. If you look at this situation, here both 5 and 6 are false. Why? Because every pig is remarkable. So this doesn't distinguish between 5 and 6. 6 doesn't distinguish between these two sentences either, because both of them come out true here. If you can see, because no pig is remarkable. So both 5 and 6 come out true. However, if you look at this situation, 5 comes out true. And well, it is Chris that makes it true, because there is at least one pig that is unremarkable. But 6 is false. And why? Because Babe is a pig, but is remarkable. And here we can see that they are different. In fact, 6 is stronger than 5, and 6 entails 5, but not the other way around. So we have seen configurations 5 and 6, but there is another place where we could put the negation, which is in front of the antecedent, and we haven't discussed that. It's this. So let's try to find its English counterpart. And to do so, let's try to follow our steps in the reverse order. What we're saying is that every x is such that if x is not p, then x is r. And a bit more English-like is everything is such that if it is not p, then it is r, which would amount to every non-pig is remarkable. But we could also phrase it as anything that isn't a pig is remarkable, or unless something is a pig, it is remarkable. And what about this one? What would 8 express in everyday English? So how would you express 8 in a way that sounds more or less natural? Well, I'll leave you to find out. Let's talk about domain restrictions. In our system, a quantifier, by default, ranges over the whole domain, over the whole universe of values. However, we often don't want to talk about the whole domain, but only about a specific subset within it. This is the case in our sentence that we're seeing here. For every x, if x is p, then r. Or every pig is remarkable. This sentence is about pigs, not about every object in the universe. So how do we restrict the domain? In this version of PL, the antecedent of the conditional within the quantifier scope, if we're talking about the universal, or the first conjunct, if we're talking about a conjunction, are the domain restrictors. So we have for every x. This quantifier represents the phrase for every x. And here the variable x is ranging over the whole domain. It ranges over the whole area inside the circle. So then we start our sentence and we have the antecedent, which is px. So we're going to put a restriction on the values of x. We're going to be concerned with those that satisfy p. So we shrink our domain to that subset of the universe that contains pigs, basically, right? So this is our domain restriction. We're saying for every x, if x is a pig, or for every x such that x is a pig, that's another way of phrasing it. And then we continue with the rest of the sentence. We introduce the consequent, which is what we're saying about pigs, about the antecedent. Here we're saying basically that pigs are a subset of remarkable things. You can represent it in this way, or you can represent it in other ways. This is just for illustration. Now, there are some quantifying expressions in English that are essentially restricted. For instance, somebody or someone or everybody and everyone, they are restricted to people. So if you have a quantifier like somebody or someone, then you're expressing a logical form that starts with there is an x such that x is a person and if you have everybody or everyone, then you're expressing every x is such that x is a person, blah, blah, blah. Or for every x, if x is a person, then such and such. So suppose you have a sentence in English that is of the form someone is r. Then in predicate logic, this is going to be there is an x such that px and rx. And if you have a sentence of the form everyone is r, then you have something of the form for every x, if x is p, then x is r. So if you have 9, everybody likes Al, what you're expressing then is for every x, if x is a person, then x likes Al. And if you're saying Al likes someone, you're saying that there is an x such that x is a person and Al likes x. And everybody who likes Beth likes Al, you represent it in this way. For every x, if it is a person and likes Beth, then that x likes Al. Nobody likes Al. For every x, if x is a person, then it doesn't like Al. Now, in some situations, I'm going to tell you to assume that the domain contains only people. In these situations, if you have something like 12, nobody likes Al, then you can simply express it like that. You don't have to include the antecedent p. The same with 13. You can also find other examples of restricted quantifying expressions. For instance, some are restricted to places. Everywhere Al goes, he is happy. And some are restricted to times. Sometimes Beth feels sad. So we can represent sentences containing everywhere with the restricting predicate lx, as in location, which we place as the antecedent of the conditional inside the quantifier scope. So we have everywhere Al goes, he's happy, symbolized like this. Here the antecedent is lx for location. gxy is a predicate x goes to y. And hxy applies to pairs of people and places, and is satisfied whenever x feels happy at y. So in logic keys, we express the logical form for every x, if x is a place, then if Al goes to x, then Al feels happy at x. And here we have the sentence, sometimes Beth feels sad, and the logical form for this would be there is an x such that x is a time and Beth feels sad at x. We could make our sentences shorter if we enrich our language by including classes of variables that are defined as ranging over particular types of things. So in this case, we could stipulate that there is a typed variable that only ranges over times. And this would read, there is a time t such that Beth is sad at t. Likewise, we could introduce a variable type that only ranges over locations. And we could represent 14 as, for every location L, if Al is at L, then Al is happy at L, instead of the awkward monstrosity we had used before. However, we won't use typed variables in this course. I was just showing you this to illustrate the ways in which we could enrich our PL language. So we're stuck with our longer, awkward symbolizations. Okay, this is all for this lesson.